We'll see. Okay, picking up where we left off on example 5, I believe, yes. BenQ erased over the night, so, you know. Okay, use the graph of the continuous function, g of x, shown below to complete the table. Now, a couple of things here. We know that the derivative of a function at a point represents the slope of the tangent line. Old news, right? Estimate the value of g prime of x for each x value in the table by drawing a tangent line through the given point of tangency, then estimate the slope. And by estimating the slope, you are coming up with the derivative. Find the y-coordinate of the point of tangency. Use the point slope formula of the equation to write the equation of the tangent line at the point. Now, tangent line approximation of f at a. This is really very much like what we've been doing. If you think, you can think of this as y equals, what do I want to say here? y1 plus m times x minus x1. That's essentially what they're doing there. When they say f of x equals f of a, so that's the y value, plus the slope, f prime of a is the slope, times x minus a, so x minus the x value. Now, the only difference is, when we write it, we usually put the y1 where? At the end. So you could also say y equals m times x minus x1 plus y1. So that whole tangent line approximation, yes, they used f of x and f of a and f prime of a, but I just want you to see that so you're not like, oh, another new formula? No, it's not. It's just an old formula written in a different way. Okay, so you need the rulers again. We need to try and be quick on this so we don't suck up a bunch of time. But when x equals -3, which point are we talking about here? That's going to be point A, if you will. Derivative estimate. Well, derivative estimate means we need to attempt a tangent line. I say attempt because, you know, so much easier on paper. I will say that. You gotta, you know. This one's a hard one for me. Nope, my tangent line curved. Okay, well, that's what you're getting from me. We're going to deal with it. So there's my tangent line at point A. Derivative estimate. I'm just from A. I'm going to rise or run until I'm about at a point. I'd say anywhere between 6 and 8. Now, officially, it's rise and then left. So negative. In my answer key, I have -6. But in all honesty, my graph here is looking more like -8. Again, these slopes are subjective, yes? Don't stress about them. -6, -8, you're in the ballpark. Happy. Point of tangency. What are we wanting there? Where is the point of tangency? That's A, which is what is the ordered pair? -3, -3. What kind of a function behavior do we have happening at this point? Increasing, decreasing, constant? Those are the type of terms I'm looking for. This is decreasing. An equation of the tangent line at x equals a? Do we just want to do this in our old form? Yeah. I think that's for the most part what I did. So y equals the slope. What slope did you use? Times x minus the x value. So it becomes x plus 3 and then minus 3 at the end. Okay. I should probably really skip some of this because we've done this, haven't we? -2. When x equals -2, What's our tangent line? It's a horizontal, yes. And so derivative, because that b is a minimum, so derivative is going to be 0. Point is -2, -6. What's the function behavior? That derivative is, or the tangent line is constant. What's the equation of this tangent line? Y equals -6 is what it ends up being, yes? Because your zero slope times those parentheses knocks it all out, so y equals -6. Okay, -0.5. When x is -0.5, that looks like that's going to be c. Nope. Okay, we're going with it. I don't exactly like it, but we're going with it. Are you getting a slope? Oh, and of course this one's in the middle of a line, isn't it? Okay. My answer key says 3. Honestly, if I look at my graph, I feel like it's more like 4. Are you in the ballpark? Point of tangency, so C is at -0.5, -2. Our function behavior is increasing. Okay. I didn't read it out loud. Do I need to read it out loud? Okay. I figure you guys can check it as you go. 1.25. Where's 1.25? Is that D? That's D. So, oh, what do we have here? Horizontal tangent line again. So that point is going to be at 1.25, comma 1. This is constant again. So my equation is y equals 1. And x equals 4. Beware, it jumps you over to point G, doesn't it? You know, we're going alphabetical all this time. Oh, hey, we're going to skip E and F. We're going to G. Ooh, big miss. I'm appreciative of a straight edge or ruler to line this up. Oh my goodness, I can't do this. There we go. Stop there. Leave it as is. My answer key, I have a slope of 7, which, because of where G is, I would count down to get to that. I would count down and left. 1, 2. If I'm looking at this one, I would say this is 8 on my screen. I'm not going by my screen, though, because I'm not using a ruler, and I'm, you know, it's rough. G is at, what, 4.3? This is increasing. And y equals, I use 7, times x minus 4 plus 3. what you need there. And let's move on. Investigating slope graphs, or F prime graphs. So this is a big AP thing where they'll give you a graph of the actual graph, or they might give you a graph of the slope, or a graph of, we'll eventually talk about something called second derivatives. And that has to do with concavity. So when you plot the motion of an object as velocity versus time, these are referred to as slope functions, or F prime graphs. In the study of calculus and physics, these graphs represent the rate of change of the original function. By analyzing these graphs, you can find where changes are occurring slowly or quickly by observing the rates of change or slopes of the tangent lines at specific moments in time. So we're going to jump into the world of F prime graphs here. So consider the function shown at right. Where are we seeing at right? It's not at right, it's down below. Okay. Sorry, confusing myself. Consider the function shown down below. Notice the curve at the first point, x equals 1/2. So they're saying this first point right here is x equals 1/2. The slope of the curve here appears to be about 1. So that red line is putting a point at 1/2, drawing the tangent line. They are saying that this slope here is approximately 1, correct? Okay. Then, at x equals 4, the slope has decreased to about 1/3. Can you analyze and sketch the slope graph on the grid below? So then over at this point, at 4, now they're saying, okay, the blue line represents a slope of approximately 1/3. That slope isn't nearly as steep, is it? So the point of that is when we first start at the beginning of this graph, the slope is more steep, yes? Like if we had to go closer to 0, that slope would be steeper than 1. Steeper, steeper, okay? As this graph goes farther out, the slope is getting less and less steep. Okay. Excuse me. So over here, first of all, let me state, your graphs will always be labeled. This is F prime graph. This right here, they never called it F, but this should have been labeled the F graph, okay? It's the actual function. So when we go to look at this F prime, or I'm even going to write on this one, slope graph. So it's going to be the derivative, or the graph of the first derivative. Now, we don't know what the first derivative is. We didn't do that math right here. We could, but not going to. So the idea is looking at the points. At 1/2, the slope is approximately 1, yes? So at 1/2, we're going to put a point at 1. The other piece we were given is at 4, there's a slope of 1/3. So what we're graphing here is we're graphing x, comma, f prime of x, if you will. It's the x value from the original graph, but then the slope. Do I dare say x, comma, m? Is that going to be confusing? F prime of a is more official. Okay. And then if we throw in a little bit more, so like, I don't know. For instance, I talked anything smaller is going to be bigger, right? Anything before 1/2, that's a steeper slope. So those values are going to be bigger up here, yes? Anything to the right of 1's like, if we look at 1, that slope is a little less steep, okay? Maybe if we look at 1, maybe that slope is 2/3. I don't know if it'd be down to 1/2 or not, but the idea is that there'd be a point above 1 that is somewhere below 1. And if you start connecting all these dots, okay, I mentioned that to the left of 1/2, they'd be up here. We'd have a curve that looks something like this. Okay, as it gets closer and closer to the y-axis, so as it gets closer and closer to x equals 0, it's going to get higher and higher because that slope is steeper and steeper. As it gets farther out here to the right, we're going to get closer and closer to slope of 0, but never actually making it to 0. Okay? So that's a little bit of an idea of a slope graph. The idea, a couple of things here. My slope graph is always above the x-axis. So that's indicating because this is always positive values, my slope over here was always positive values. Okay, this is indicating as we go farther out, my slope is getting smaller, which, as we talked about, this is becoming a flatter and flatter line. Okay, let's look at example 7. Comparing the graph of f to the graph of f prime. So notice it's labeled, yes? Always look for those. It is so easy to overlook them and not know what graph you're looking at. And it sounds silly right now, but think farther out with me, okay? So as we compare f to f prime, trying to decide where I want to start here. For instance, if we look here, what is that about? When x equals -1, what do you notice there? This is a max, there's a horizontal tangent line, so what would that mean there? Slope is 0. So what's that mean over here? At the point -1, we have a slope of 0. Do you see that connection? Interesting. A max in the graph is a 0 on the slope graph. Is there a minimum here we can look at? There's a minimum about 4, maybe a little bit past 4. What do you know about a minimum? It has a horizontal tangent line, yes. It has a slope of 0. What do you notice over here? On the slope graph, when x equals 4, or a little bit past 4, whatever value that is, then we have a point at 4, 0. Do you see the connection? So what am I trying to point out here? Mins and maxes on the original graph are zeros on the slope graph. We talked a little bit yesterday about concavity, right? I need to look ahead in the notes and see if she introduces concavity better or not, because it's just kind of all of a sudden thrown in. But this graph, it starts off being concave down, yes? And then at some point it changes and it is concave up, correct? Well, somewhere in here, I don't exactly know where, but somewhere in here, there's a spot where our graph changes concavity. And that is called, the notes used POI as in point of inflection. I usually say IP as in inflection point. Okay. But this is an inflection point. Inflection point is where my graph changes concavity. Inflection point. So that's what I used for IP, where graph changes concavity. Make sense? Okay, a little bit of vocabulary there. So my mins and max became 0. What's my inflection point become? Inflection point somewhere between 1 and 2. What do you know is on the slope graph here? Between 1 and 2, where am I? That is a min. And so the idea here, as we change from concave down to concave up, we have a minimum. Now, what I need to figure out is how in depth am I supposed to be going here? Let me read what all is said here because I'm trying to remember. The f prime graph gives us insight into the behavior of the original function. For example, at x equals 1, the slope appears to be almost negative 2. Therefore, on the derivative graph, the value at x equals 1 is almost negative 2. There are several relationships between the two graphs that are particularly important to note. Let's explore these in depth. Okay, so I've mentioned several of these. I think we'll look at them on the next page. Okay. Because the only other thing that I was thinking about I could point out here is this is concave down here, yes? The fact that this graph is concave down, notice in the same interval over here, this graph is what we would call decreasing. Remember, decreasing is as we, from left to right as you go down, as your values decrease, this is decreasing. Over here where my graph is concave up, what do you notice about the derivative? It is increasing. Those are connections that we're going to be making. And I think it looks like we make those connections more on the other page.
Could your inflection point ever be like a max, or is it always going to be minimum?
It could be a max.
Okay.
If this graph was upside down and you had concave up first and then concave down, this parabola would be flipped. So yes, valid point. What this minimum does is it indicates that it's decreasing first and then increasing second. And so that's concave down to concave up. If you had concave up first and then concave down, it would be flipped. Okay, let's look at the next page. So kind of continuing on. When the graph of a function is rising, we will say that the function increases. That's just alluding to that, right? When the graph is falling, we say the graph decreases. It's customary to read a graph in much the same way as we read a book, from left to right. I taught this to you a year ago when I taught increasing and decreasing in pre-calc. And I say a year ago because guess what I'm teaching in pre-calc today? Increasing and decreasing functions. Okay, so as you go left to right, if your graph is going up, it's increasing. If your graph is going down, it's decreasing, but always left to right. Now, starting at the left, on the graph of f of x, state the intervals of x where the graph rises. What do you notice about the slope of the curve on these intervals? So I guess we're flipping back and forth here. You guys are we'll open our, easier for you guys. I'm just going to open my notes here so I can see both pages. Okay, so looking at the graph of f, so we're looking at the first graph here, yes? Intervals where x rises. Where's x rising? Negative infinity. So as it's going off to the left, negative infinity, where does it stop rising? That negative 1-ish. Okay. And then before I flip to my other page, then we start decreasing. Do we ever increase again? Yeah, when do we start increasing again? About 4 to infinity. So f of x increases. I'm going to say negative infinity to negative 1 and 4 to infinity. I've written down 4.2 on my notes because when I looked against Ansky, that's what she used. But 4 in that vicinity, right? Now, it asks what you notice about the slope. On those two increasing sections, what do you notice about the slope? What is the slope when you look back there? If it's increasing, my slope is positive. So increasing graph has a positive slope. Next part, starting to the left, state the intervals of where the graph falls. What do you notice about the slope of the curve on these intervals? So f of x is going to decrease where? I can almost do it without looking back. Because we had two increasing intervals. Where's the decreasing interval? -1 to 4? Because it was in the middle, yes? What do you notice about the slope on this section? It's negative, yes? And I am shorthanding here. I'm not going to try and fit a bunch in, but, you know. I'm not always one to use complete sentences. I try better for calc, but I'm not one to do it. However, on AP, you are expected to be able to explain. That's the key. And complaining like, not that it has to be complete sentences, but complete thoughts. And slope, arrow, negative. Okay, good enough for me in class. Is that good enough for AP? No. It'd need to be more along the lines of the slope of the graph is negative. Or the slope of the graph on the interval -1 to 4 is negative. You know, you want to be wordy there. You want to put the details in. Okay, C. At what values of x on the graph does a function appear to have a maximum or minimum? What is the slope of the curve at these points? And what characteristics on f prime occurs at these points? We already did this. We just have to put it in writing. So see if you can go back and figure it out. So, okay, first question. At what values of x does the function appear to have a max or min? So, and I'm going to use the word relative because this wouldn't be an absolute max or min. It would be a local or relative. There's a relative, what do you want to do first? The max came first, didn't it? Where's their relative max at? When x was approximately -1? And there's a relative min where? At x equals 4. What about the slope at these points? Min, max, the slope is always going to be 0, yes? Slope of curve is 0 at these points. And I didn't leave myself room. What characteristic of the f prime graph occurs at these points? Okay, when the slope is 0, it creates a 0 on the graph, yes? Okay. Or x-intercepts. Okay. We already talked about this too. Now look carefully at this one. Why does the graph of f prime reach a minimum value near x equals 1.5? Okay, inflection point, right? So at 1.5, my concavity changes from concave down to concave up. Can you explain what is occurring at x equals 1.5 in the graph of f of x to create this minimum on the slope graph? Changing concavity, yes? Okay. So at x equals approximately 1.5, there is an inflection point. So I've always seen IP, or I've always used IP, but there's also POI, point of inflection. So there's an inflection point, and I'm going to say where graph is changing from concave, which was it? Concave down to concave up. Okay. Next page is what's going to take our time, is getting the connections here. Because on the next page, we're going to sketch our own f-prime slope graph from a given graph. Now, a couple of points of procedure here. Describe how the slope changes from left to right along the curve. Notice the intervals where the slope is positive, negative, or 0. And then we're going to write down the changes as they occur from left to right on a number line. Notice where the x-intercepts occur. Pay attention where the function is above the x-axis or is in positive, and where it is below the x-axis, negative. Okay. So, we have this graph here, yes? Let's talk. Who do I want to talk first? So let's start by talking about decreasing and increasing. What do we notice here? What are we doing first? Decreasing. We're decreasing to what value? Approximately x equals -2. And I guess I'm always talking in terms of x's right now. Okay, so we are decreasing to x equals -2. So as we think about this, on my number line here, I'm going to set my number line up so we're talking about what's going on G on top and how that's going to relate to G prime, the derivative on bottom. So at -2, what physical feature do we see on this graph? We see a minimum, yes? What were we doing before we got to that minimum? We were decreasing. Okay? Continue the next part. What do we do after we finish decreasing? We are increasing. What value are we increasing to? It's not exactly 3, is it? You want to use 3 or you want to be a little more specific? 3? As long as you realize it's not officially 3. Okay. So to get to 3, we were increasing to get to 3. What is that at 3? That is a max. And what do we do after 3? Again, you are decreasing. Okay. Now, let's talk G prime. On the given graph, there's a min and a max. What are those going to be when I draw my derivative? Those are going to be zeros, yes? Do you see how I'm trying to pair all this information up? Okay. Decreasing. When my original graph was decreasing, what does that mean about my derivative? And so when the graph is decreasing, what kind of slope is that? It's a negative slope. And so what's the derivative going to be? It's going to be negative in this area. Negative on a graph just means it's below the y-axis. Or excuse me, below the x-axis. How can you be below the y-axis? Don't ask. Okay. So any place my graph was decreasing, my derivative is going to be negative. Because a decreasing graph is a negative slope. So what's that mean about the increasing portion of the graph? It had a positive slope, so it's going to have a positive. And you guys realize when I say zeros, I mean x-intercepts, yes? Okay, I think that's all the pieces that I needed to connect there. Okay, so go over to this graph. I'm going to have a 0 at -2. We're going to use a 0 at 3, a little bit to the right of 3, if you will. Before I continue, I'm going to do this one more time. On that first number line, we kind of talked about increasing, decreasing. On the second number line, I want to talk about concavity. So, what is my graph to begin with? It is currently at the beginning, it is what? This is bold up. So if it's bold up, this section is concave up. Does that make sense? Okay, so my graph at first is concave up. Oh, I didn't realize it was an orange. And then what happens? At some point, my graph changes, and then what? It's bold down, and it's concave down. Approximately where does that change? Somewhere in here? I don't have an exact value. A little bit before 1? 0.5? 0.75? I don't know. But does concavity change there somewhere? Okay. We want to be nice, neat number. How about I use 0.5? So my graph changes from concave up to concave down. And at that 0.5, there is an inflection point, or point of inflection. Okay? IP is the same thing as POI. When it's concave up, my graph is concave up, what's this graph going to be doing? Is my question making sense? We didn't talk about it on this page. But, so, if we go back here, my graph at first was concave down, yes? What was my graph doing here? It was decreasing. Then my graph went to concave up. What's my graph doing there? Increasing. So, on this one, my graph was concave up. So it's going to be increasing. And then when it's concave down, it's going to be decreasing. If your graph is increasing and then decreasing, what happens between increasing and decreasing? There's a max, right? If you're increasing and then you decrease, you have to go past the top of the mountain. So at this point, there is a max on this graph, on the derivative graph. So, do we know how high that goes? No, we don't have a value for how high that goes. But if you put this all together here, so somewhere here, there's going to be some kind of max. So my graph is negative before we get to 2, -2, excuse me. Okay, my graph is negative before I get to -2, so I'm starting down here. At -2, we cross through the 0. My graph is positive between -2 and 3, so up here I'm above the x-axis. And then it's negative after I get past 3. At the same time, we're increasing up to 0.5, and we're decreasing after it. So what am I drawing here? We get the upside down parabola this time. I think Ethan was foreseeing the future here. This is what you asked pretty much, Ethan?
Yeah.
And as you can tell, I'd forgotten what the next problem was, so I didn't remember that we were foretelling the future. Okay, you know what? I think we've already done this part. Okay, ABC was just telling us what to do, I think. Mark the number lines above to show values where g of x changes from increasing to decreasing. At these x values, the slope of the curve is, So when we change from increasing to decreasing, the slope of the curve is, they're wanting 0 there, right? Yeah, 0. On the function, we refer to those values as, do you remember the word extrema? Extrema are maxes and mins, yes? Okay, so remember that word extrema. Maxes and mins. Notice how the graph changes from concave up to concave down. We did that over here on the right. Estimate x values where this occurs. Place this value on the number line to the right. You will see that this will become either a max or min on the graph of the derivative. This is commonly known as the point of inflection. Again, I always just say inflection point. Point of inflection. Difference in people. And then use your summaries to create the graph of the derivative function on the right. We did that. Okay. This next page is going to seem pretty familiar, I think. So we can probably get through it, but if we don't, this was the big stuff, right? And I'm going to tell you guys, this is probably an area I'm weaker in, is being able to go back and forth between these. But it is a huge thing in AP. So the more you can work to understand these connections and how the first derivative, increasing, decreasing, connection with concavity and the mins and maxes and the zeros and all of that, the better off you'll be. Okay? So not something to brush under the table and think, man, I hope that never comes back. It's coming back. Okay? That's, there's some things like, okay, are you going to have to draw tangent lines and figure out the slopes? No, not really. I mean, you might have to estimate a little bit, but not like what we've been doing. Okay, one last thing before we go. We've seen that it's possible to estimate the numerical value of a derivative at a single point by finding the slope of the secant line passing through 2 points on the graph. Let's explore how this can be done using a table of function values for a continuous function. This is what you did the other day in homework. Use the table values to find the derivative for each x value, describe the behavior of the function, and explain your reasoning. Now, then again, AP likes to use tables. Okay? Not unheard of by any means. So, x equals a when x equals -2. So, in order to do the derivative around x equal 2, when we're doing the, where did it say it, the slope of the secant line, what do we want to use? I helped several of you with this the other day. You want to use the value on either side of it. So we're going to use the -4, -6, and -1, 4. And we're going to find the slope. Or in other words, I'm going to say f prime of -2. I'm doing 4 minus -6 over -1 minus -4. Ten-thirds. Okay, based on that information, what is my function doing at this point? My derivative is positive, so my graph is increasing. Justification. Why is it decreasing? Because the slope is positive. Now, how do we say? So if I say at the point, what was my point? -2, 2. In order to say the slope is positive, I'm going to say f prime of -2 is greater than 0. Is math speak for positive? A little bit of algebra in here. Okay. Yes?
Why is the 4 negative?
This 4 here?
Yeah.
Because it's my y value 4 right here. 4 minus -6, -1 minus -4. Grabbing the wrong value?
Yeah.
Easy to do, easy to do. So you guys should see how many mistakes I do this when I'm going through these notes for the first time. It's not good. Okay, so when x is -1, what are we doing now? using those 2 points on either side. So f prime of negative 1 I just got negative 3/2. Did you get negative 3/2? So a negative slope means my function is decreasing. And justification, how do we know it's decreasing? And that is because the slope at negative 1 is negative, less than 0. So right here, I'm saying slope is negative. On the last one, I was basically saying slope is positive. At x equals 0. So the derivative, or excuse me, the slope around 0, 4 minus 4 over 2 minus negative 1, and we get what? 0. What do you know when the slope is 0? My graph is going to be, when the slope is 0, the function is constant, as in the slope of the tangent line is a constant, correct? Because it's a horizontal line. Now, our justification is because the derivative of 0 is equal 0. We'll come back here in a moment, assuming I remember, and talk about what's happening at that point. In other words, basically, if the slope is 0, that means there's either a min or a max. Which is it? And we'll come back and talk about it in a moment. Okay, 2. Around 2, what am I using? 0 and 3. So f prime of 2 Did I get 1? Keep checking my math. 1 is positive, so that is, my graph is increasing there. And that's because the derivative at 2 is greater than 0. In other words, my slope is positive. Now, how caught up are we? Because what I want to do, I have one more to do, I know, but when my slope is 0, that's either a min or a max. Which is it here? What was my graph doing to the left of this point? It was decreasing. What was my graph doing after this point? It was increasing. So what is that? That's a min, yes? So this right here is a relative minimum because you decrease down to it and you increase away from it. And so that would make it a minimum. Okay, I've got one more here, right? F prime of 3. I got a slope of negative 2/3, which tells me decreasing because my slope at this point is negative. We have a couple blanks to fill out at the bottom here, right? Okay. If f prime of x is less than 0, then the graph of the function is what? What is the graph doing at that point if the derivative is less than 0? It is decreasing. So the next sentence then, if the derivative is greater than 0, then the function is increasing at that point. A relative maximum occurs on a function if f prime of x equals, a maximum or minimum occurs when the derivative equals 0, and the derivative changes from blank to blank. So we did a minimum here, and our derivative changed from negative to positive. So what's a maximum going to be? When we change from positive to negative. And on the flip side, a minimum occurs if the derivative equals 0 and the derivative changes from negative to positive. Something crazy just happened.
You made
The
it
bell didn't ring on me.
easy.
I don't feel like I pushed